Okay, in this lecture video, we're going to talk about how we identify electrons within an atom. Which ones are we talking about specifically when we have a multi-electron atom? So we identify atoms by how much energy they have. Sorry, not atoms, electrons. We identify electrons by how much energy do they each have. And the first thing to note is that the farther from the nucleus that an electron is, the more energy it has. So electrons farther from the nucleus have more energy. And based on this, we can give each electron an address to know which ones we're talking about. And we can even use an analogy to real addresses. So the way we'll start our analogy is we'll consider our atom, whatever atom it is that we're talking about, as our country. Okay, so identifying the country. And within that country, the first thing that we want to talk about is the energy level that we're in. And the energy level is represented by an N. And in our address lingo, this would be the equivalent of what city is that electron living in. It's sort of the general energy of the electron. And N is an address type identifier, so it goes from 1, 2, 3, 4, 5, etc. So it's not like saying it has an energy of 1. It's just the address, so an energy level. So there is a particular energy associated with energy level 1, for example. So if we were to make a sketch showing these energy levels N are sort of arranged about the nucleus, we could make our sketch with the electron cloud like we did before. So we have our nucleus in the middle, and then surrounding it is that electron cloud. And we know that as you go farther and farther from the nucleus, N increases. The energy level increases. So energy level 1, represented like that, has less energy than energy level 2, which is less than energy level 3, etc. Okay? We can also make another sort of representative model of what this is like. So again, we could start with our nucleus in the middle, and then we could draw energy levels around it, represented by spheres. And within this, we could say, well, here's energy level 1, and so electrons anywhere within this area would be energy level 1. This region would represent energy level 2, so any electrons in this area would be energy level 2, and energy level 3, and so on and so forth. Because in this representation, we still have N increasing, so the energy level is increasing as those electrons get farther from the nucleus. But it's important to remember that these are just models. This picture here, this one, that's just a way we represent on paper how far electrons are from the nucleus. It doesn't mean that they're in some sort of sphere. It doesn't mean that they're traveling in a circle. It doesn't mean any of that. It's just a way for us to keep track for electrons in a particular energy level about how far from the nucleus do we think we would find them. Okay, so that's the city address of our electrons within the country that is our atom. So now let's look at the part of our address. Oops, I don't want to write in blue. So within this energy level N that we're talking about, we want to know the specific amount of energy within that level, whatever N is. And we call these energy amounts sublevels. And just like we represent the primary energy level with a letter N, we represent sublevels with letters as well. And those letters are S, P, D, and F. So this type of the address within our analogy that we're using, this would be the dwelling. Okay, so for humans that live within a city that's within a country, we live in some sort of dwelling. So that dwelling could be a tent, for example, could be a house, it could be a mansion, it could be an apartment building, etc. So we know for these dwellings, they're all different shapes and sizes. And the same is true for the sublevels that electrons inhabit, the S, P, Ds, and Fs. But within each energy level N, there are only certain sublevels that are available. So that kind of makes sense, right? In every type of town you go to, there may not be mansions available for people to live in. So different cities or different energy levels have different sublevels or dwellings available to the electrons. So let's make a list of what those are. And we're only going to go for primary energy levels N, where N is 1, 2, 3, and 4. So the corresponding sublevels for that, so if you're in energy level 1, there's only one type of sublevel, and that's an S. In energy level 2, there's two. There's an S and there's a P. 3 has an S, a P, and a D. And 4 has S, P's, D's, and F. So we can see that as we get farther from the nucleus, right, as our energy level increases, there are more and more sublevels available to us because there's just more room. The farther you get from the nucleus, the more room you have for different types of sublevels. Now, each of these dwellings has different numbers or shapes within them. Or at least we could use our analogy as rooms within our sublevel. So within our analogy that we're using right now, the next level of identification would be what room are we in? So each sublevel has different types of rooms where those electrons could reside. So let's take a look at what those are. So the first sublevel, which is S, has a corresponding shape to it, and that's a sphere. Okay, and there's only one kind. There's just one type of S sublevel. So let's look at that orbital looks, or sorry, I'm already jumping ahead of myself. Let's look at what that sublevel looks like. So here it is. So the nucleus of this atom would be smack dab here in the middle, and it's surrounded by this spherical shaped S orbital, or sorry, I did it again, S subshell. And so within this sublevel or subshell is where we would find some electrons. And we'll figure out how we know which electrons are where later on in the semester. But all of the S sublevels look like this. They're spheres. So now let's look at the sublevel, and that's a P sublevel. And it has kind of a wonky shape. It looks like kind of like a dumbbell, like that. And there are three of them. So there are three different types of P sublevels. There's a P called P sub X, P sub Y, and P sub Z. So let's take a look at what they're like. So here they are, PX, PX is along the x-axis, PY is along the y-axis, and PZ is along the z-axis. So you don't have to remember that. But what you do need to remember is that they're kind of shaped like dumbbells, and each dumbbell is in a different orientation around the nucleus of the atom, which again is in the middle here of our coordinate system. So in this case, it would be like saying you have three different room options. You have a kitchen, a bedroom, and a living room, for example, because remember, these sublevels represent the rooms within the dwelling that we're living in. So when you're in a P type of sublevel, you've got three room options. Remember back to the S type of sublevel, you only got one room option. Okay, but in P you have three. The next level that we have is the D sublevel. And I can't even draw a picture of that. So let's take a look at it. So here they are, and you can see that there are 5 kinds, right? So you've got 4 that are sort of oriented as like, I don't know, what are these? Like 4-leaf clover type of things. And then you've got this one real weird one that's like a dumbbell with a donut around it. So within these shapes, again, are where the electrons can reside. And if you're in a D sublevel, then you've got 5 different rooming options. Okay, so before we had 3 different rooming options, and before that we had, in the S sublevel, we only had 1. Okay, so let's look then at the final type of sublevel that you can have, and that is the F sublevel. So if we had 1 S type of sublevel, 3 P sublevels, 5 D sublevels, hopefully you're guessing that there are 7 different kinds then of F sublevels. And as you can see, the shapes get even crazier and crazier. So here we have 7 different options for where electrons could dwell. 7 different option types, I should say, if they're in an F sublevel type of a room. So the thing about this are sometimes these pictures are kind of misleading. So let's just look again at a p orbital, just one of them. Oops. So here's a p orbital. So when we look at this, we have to remember that electrons, they don't obey the laws of physics, right? So we're used to thinking about things like the Earth, and there's the moon that orbits around the Earth, right? And at any given time, scientists can predict exactly where the moon will be, or the Earth revolves around the sun, those types of things. Or these sublevels aren't like that. Instead, what these mean, these sublevels, is that they're just a region around the nucleus. So I'll put my nucleus back on here. There it is. Where the electrons might be found. Okay? So the first thing to know is that this shape, this dumbbell shape, represents the region where the electrons might be contained within the sublevel. So they would be contained either within this lobe of the dumbbell or within this lobe of the dumbbell. Okay? So they're not on the surface of the dumbbell. I mean, they might be, but that's not what the shape means. It means they're contained within it. Okay? It doesn't say anything about the motion. There is nothing to say that the electrons, like let's say there's an electron right here. I'll show it in red. There's nothing to say that this electron is moving in any particular direction. In fact, at some given point in time, that electron might be there, and then all of a sudden, that electron might be over here. In fact, that electron could be here and here at the same time. Electrons seriously make up their own rules. Okay, they obey the rules of quantum mechanics. And that's not something that we can visualize on our level. It's nothing that you can look at and understand. So the best we can do is model it. So this sublevel shape is a model that represents the energy of some electrons that might be found within it. And we'll talk more in class, a lot more, about what these shapes represent, why the walls are fuzzy. So for example, even though it looks like we're drawing a hard sort of shell here, and we keep calling it an energy shell or an energy sublevel, the walls are fuzzy. There's nothing about this shape that prevents this electron from being found instead of where it's at right now. Instead being found out here, right? So this is just a model that lets us represent how much energy the electrons have. The last thing to remember is that with these models, with these S, P, D, and F sublevels within the energy levels, these shapes can each hold 2 electrons per sublevel shape. Okay, so just to summarize, so we have the primary energy level, and that's N. And within that primary energy level, we have different sublevels, and there are a different number of each sublevel. So for S, there is 1 of them. For P, there are 3. For D, there are 5. And for F, there are 7. And each one of these sublevels can hold 2 electrons each. So that means you can have a total of 2 electrons in an S sublevel. For P, since there are 3 different kinds of P sublevels, you can hold a total of 6 electrons in the P sublevels. For D, since there are 5 different versions of D sublevels, you can hold a total of 10 electrons. And for F, you can hold a total of 14 electrons. These are E's for electron. And again, we'll go over more about what these energy levels and sublevels are during class.